welcome you all to this digital classroom for the subject control system. In the previous lecture, I gave you a brief introduction about root locus and we discussed about angle condition and the magnitude condition, which are the most important criteria for root locus analysis. Today, we are going to define few of the rules related to root locus. Rule number 1 states that the root locus is always symmetrical about real axis. The roots of the characteristic equation are either real or imaginary or combination of both, in the sense they are complex conjugate also. Therefore, their locus must be symmetric about the real axis. The image shown here is one half of the butterfly and the other half looks exactly the mirror image of the other. Hence, you can see that it is symmetric. Similarly, in the S-plane, if you represent the locations of the poles on the real axis and the complex conjugate poles, which appears as a mirror image in the S-plane, and if you vary the parameter k in the characteristic equation and the roots will change its location, and we are very sure that it will be symmetric with respect to real axis. This is an example of a root locus in which the one half of the root locus looks exactly the mirror image of the other. Hence, we can say that the root locus is symmetric with respect to the real axis. Let us define for rule number 2, which states that as k increases from 0 to infinity, the number of root locus branches starts at open loop poles of G of S and ends at open loop zeros of G of S, while P minus Z branches terminate at infinity along the asymptotes. Justify the statement first, then let us prove the statement. Let G of S into H of S represents the open loop transfer function and P represents the number of open loop poles and let Z represents the number of open loop zeros. You might encounter 3 different cases in which the number of poles can be greater than the number of zeros. If P greater than Z, we can say that the number of branches will be equal to number of open loop poles, that is N will be equal to P, and we call it as a proper transfer function. And on the other side, if P less than Z, number of branches will be equal to the number of open loop zeros, that is N will be equal to Z, and we can call it as an improper transfer function. And finally, with respect to case 3, the number of poles will be equal to number of zeros, and hence we can call it as a strictly proper transfer function. And in this case, all branches from P poles will be terminating at Z zeros. If P greater than Z, all poles will be terminating at Z zeros and the rest of the P minus Z branches will be terminating at infinity. Let us prove the statement. The open loop transfer function is given by k into n of s divided by d of s, where n of s represents the open loop zeros and d of s represents the open loop poles, the numerator polynomial and the denominator polynomial. The characteristic equation is given by, from the transfer function, c of s divided by r of s is equal to g of s divided by 1 plus g of s into h of s, from which we can write a characteristic equation as 1 plus g of s into h of s is equal to 0. Now let us substitute for GFS in this characteristic equation. And we know that the characteristic equation is nothing but the denominator of the closed loop transfer function. Hence, we can call it as closed loop poles. Once after substituting for GFS, we get 1 plus k into n of s divided by d of s equal to 0. Further simplification, I get d of s plus k into n of s equals to 0. In which d of s we know that it is open loop poles and n of s is open loop zeros. And here it is very clear that the closed loop poles can be represented in terms of open loop poles as well as open loop zeros. Now we are going to change the value of k from 0 to infinity, and let us look into the results. When k is equal to 0, let us see what happens to this characteristic equation. Once after substituting for k equal to 0, I get d of s is equal to 0, which is equal to the characteristic equation. Hence, it is very clear that the open loop poles is equal to the characteristic equation, that is closed loop poles. Hence, at k is equal to 0, it always starts with the open loop poles. Whereas, when k is equal to infinity, let us again substitute in the same characteristic equation and let us look at the effect. Once after substituting for k is equal to infinity, before substitution, let us rearrange the equation as d of s is equal to minus k into n of s. Hence, k will be equal to minus of d of s by n of s. Once after substituting for k is equal to infinity, I get n of s is equal to 0, which is equal to the characteristic equation. Hence, it is very clear that when k is equal to infinity, the characteristic equation is equal to the open loop zeros. Hence, when k is equal to infinity, it is very clear that the characteristic equation is equal to open loop zero. And this is the reason in which the rule has been stated as for n number of branches, it starts from open loop pole at k is equal to 0 and it terminates at open loop zeros at k is equal to infinity. And this has been proved here. Let us take few of example and justify the statement. So for the same rule, I have taken an example. G of s is equal to k divided by s into s plus 1 into s plus 2. From here, it is very clear that we don't have any open loop 0 in the numerator. We have three poles. That is s is equal to 0, s is equal to minus 1 and s is equal to minus 2. I have written p is equal to 3 and we don't have any zeros in this equation, hence z is equal to 0. And in the beginning, we have stated with three cases in which p greater than z. Hence, the number of poles will be equal to p. I have written here n is equal to p is equal to 3. As the number of poles is equal to 3, the number of branches will be equal to 3. And let us recall the statement for rule 2. The number of root locus branches n starts from open loop poles p and ends at open loop 0 z. In this case, as z is equal to 0, we don't have any 0 to end up. So let us continue reading the statement. While p minus z branches terminate at infinity along the asymptotes, which means that as we don't have any zeros to terminate with, we have to take p minus z branches, which is going to terminate at infinity. P minus z in this case will be equal to p is equal to 3 and z is equal to 0. Hence, all the three branches will be approaching to infinity. Let us plot these poles in the S-plane. We have three poles at s is equal to 0, s is equal to -1 and s is equal to -2. We know that we used to represent the pole in a cross mark. Now, with respect to rule 2, all these poles will be terminating to infinity. It will be at 0 when k is equal to 0. And for the pole at s is equal to -1, it remains in -1 at k is equal to 0 and it reaches infinity when k reaches infinity. Similarly, for the pole at s is equal to -2, it will be at this location when k is equal to 0. And when you keep on varying the value of k, it reaches to infinity when k approaches infinity. So all the three branches which is originating from these three poles will be terminating to infinity. Let us take another example. And in this example, the number of poles p is equal to 2 in this case, and we have 1, 0 at -1. So let us recall the statement for rule 2, in which it starts from open loop poles and it terminates at open loop zeros. As we have 1, 0 to map with, one of the pole will be terminating at 0. Here in this case, it starts from open loop pole at -2 and it terminates at open loop 0 at -1. And for p minus z, that is p is equal to 2 and z is equal to 1. So p minus z branches, that is the rest of the branch which is going to start from the pole at s is equal to -3 will terminate to infinity. This is the case in which p is greater than z. Let us take another example in which the number of poles equals to number of zeros. Then we know that p is equal to z, which is a strictly proper transfer function, and all the poles will be terminating at zeros. Let me highlight it with a different color. So in this example, it starts from an open loop pole and terminates at a 0. And similarly, for the other pole, it starts from this open loop pole and it will be terminating at 0. So in this case, none of the pole is going to terminate at infinity as p is equal to z. So almost we have analyzed for different cases and we have justified with rule number 2. Let us move on to the next rule. Rule number 3. It states that on the real axis, the loci is nothing but the plural of locus. The loci are to the left of an odd number of poles and zeros. Let me read it once again. On the real axis, the loci are to the left of an odd number of poles and zeros. Let us justify this statement. That is, let me take few examples in which we have to check for whether we have any odd number of poles or zeros towards the right of the point which you're trying to trace. If it is yes, then the root locus exists to the left of an odd number of poles and zeros. If it is no, then root locus does not exist. Let us take few examples and justify this. With respect to real axis, in this example we have 3 poles and 2 zeros. First, let me number it. So we have total of 5, 3 poles and 2 zeros. Now let us take a point exactly at this location. Now we have to look into the right and inspect whether we have any odd number of poles or zeros towards your right. Yes or no? With respect to this case, it's no. No, I don't have any odd number of poles or zeros in this case. Hence, root locus does not exist in this region. I can make it as NRA. Now let us assume that you have taken a point exactly in this location. Now just look into your right side. Again, read out this question. Can you able to see any odd number of poles or zeros towards your right? Yes, I could able to see one pole towards my right. Hence, the root locus exists to the left of an odd number of poles and zeros. Hence, here the root locus exists towards the left of an odd number of poles or zeros. Now, let us assume that you are at this location and look towards your right. Repeat the question once again. Can you able to see any odd number of poles or zeros towards your right? No, I could able to see even number, that is one pole and one zero. Hence, no root locus exists in this region. I can write it as NRL, and this region is RL, and this region is NRL. And there will not be any region of root locus until this region. Now let us assume that exactly you are at this point. Now look towards your right side. Can you able to see any odd number of poles and zeros towards your right? Yes, I could able to see odd number of poles and zeros. I could able to see 3 poles towards my right when I am in this position. Hence, root locus exists towards the left of an odd number of poles or zeros. Now let us assume that you are at this location. I can write here as RL. Now you are here at this location. Look towards your right. Ask the question once again. Do you have any odd number of poles towards the right? No, I don't have any odd number of poles. I have 4 poles and zeros. Hence, root locus does not exist in this region. I can write it as NRL. Now let us assume that you are at this location and look towards your right side. Ask the same question once again. Can you able to see any odd number of poles or zeros towards your right? Yes, I could able to see 5 number of poles and zeros towards my right. Hence, root locus exists towards the left of an odd number of poles and zeros. And this is how you have to highlight the existence of root locus on the. Let us take few more examples and justify the statement. This is another example in which I have only one pole. You can follow the same procedure. Take a point at this location. Look towards your right. We don't have any odd number of poles and zeros. Hence, NRL root locus does not exist. Now take a position at this point to, and you can look towards your right. Ask the same question. Can you able to see any odd number of poles or zeros towards your right? Yes, I could able to see an odd number of pole. Hence, root locus exists to the left of an odd number of poles and zeros. Let us take one more example. 3 zeros and 1 pole. Again, you can ask for the same question and we can identify that we have total of 4 and root locus exists between 2 and 1 and between 4 and 3. Hope you have got a very clear idea with respect to rule number 3, as we have taken many examples to justify the statement. And the angles from the real poles or zeros are 0 degree if the test point is to the right. That is, if you wanted to measure the angle for any pole or zeros, if the test point is to the right side, that is, if the test point is towards the right side, then the angle will be 0 degree. If suppose the test point is towards the left, then the angle will be 180 degree. Now let us mark the existence of root locus for an example which has poles at s is equal to 0, s is equal to -1 and s is equal to -2. So take any point on the real axis, look at the right side. Can you able to see any odd number of poles and zeros towards your right? No. Hence, root locus does not exist. Now take a point in this location. Look towards your right. We have one pole towards the right. Hence, root locus exists towards the left. Similarly, root locus exists from -2 to infinity. Let us move on to the next rule. Rule number 4 and 5. For large k and s, p minus z of the loci are asymptotic to lines at angle theta, radiating out from the point s is equal to sigma on the real axis, where theta is equal to 2q plus 1 into 180 degree divided by p minus z, where q is equal to 0, 1, 2 extended up to p minus z minus 1. And theta is nothing but the angle of asymptotes. And sigma, we call it a centroid, that is the center of the asymptotes, which is given by summation real part of poles minus summation of real part of zeros divided by p minus z. So rule 4 and 5 states about the angle of asymptotes and the plot of the centroid, that is the center of the asymptotes. So this rule is very simple. From the given open loop transfer function, we have to calculate for sigma and theta. Let us take this example in which g of s is given by k divided by s into s plus 1 into s plus 2. Hence, we have three poles at s is equal to 0, s is equal to -1 and s is equal to -2. We know that the angle of asymptote theta is given by 2q plus 1 into 180 degree divided by p minus z, where q ranges from 0, 1 to extended up to p minus z minus 1. In this case, p is equal to 3 and z is equal to 0. Hence, we get q ranging from 0, 1 to 3 minus 1 is 2. So, q is equal to 0, 1 and 2. Hence, we get 3 asymptotes in this case. Let us substitute for q is equal to 0 in this expression. We get theta 1 as 180 degree divided by 3, that is 60 degree. Substituting for q is equal to 1, theta 2 will be equal to 180 degree. Substituting for q is equal to 2 in the above expression, we get theta 3 is equal to 300 degree. So we have 3 asymptotes at an angle of 60 degree, 180 degree and 300 degree. The next step is to find the centroid, in which centroid is given by summation of real part of poles minus real part of zeros divided by p minus z. As we don't have any zeros, we can exclude the second term, whereas we have 3 poles and all are real. Hence, sigma will be equal to 0, -1, -2, minus of summation of real poles of zeros, the whole divided by 3 minus 0. Hence, centroid is equal to -1. Centroid is nothing but the center of the asymptotes. So now we have to plot the angle of asymptotes in the S-plane with centroid as the reference. So let us plot this in the S-plane. We have taken the same example of G of S. Already we have plotted the poles and we have determined the existence of root locus. We have applied rule number 1, 2 and 3 also in this case, and we are following up with the same example. Here sigma is equal to -1. Let me mark the centroid exactly at -1. Sigma equals to -1. And let us make use of the protractor, and with sigma is equal to -1 as a reference, we have to plot for 60°. Exactly, I have plotted for 60°. Take a pencil, mark for 60°. Then theta 2 is equal to 180°. Let us mark for 180°, making use of the protractor, with sigma is equal to -1 as the center. And theta 3 is equal to 300°. To mark for theta 3 is equal to 300°, this angle is 180°, this is 190, and this is exactly 270. This will be 280, then 290, and this will be exactly 300. Let us mark for 300°. Once after marking for theta 1, theta 2 and theta 3, let us draw the asymptotes. Let me take the scale and mark the asymptotes at an angle of 60°. The plot is here, 60° plot. We have already marked 60°, making use of the protractor. Now we are going to join the centroid and plot the angle of asymptotes. Similarly, let us plot for 180° as well as 300°. With sigma is equal to -1 as center of the asymptotes. Now let us draw for 300°. Now with sigma is equal to -1 as center, let us mark for the angle of asymptotes exactly at 300°. Now this angle is 60°, and this angle is 180°, and this is exactly 300. Let us mark the angle as 60 degree, 180 degree and 300 degree. Hence, we have done with all the 5 rules and we have justified it taking many different examples. In the next lecture, let us discuss about rule number 6 and 7. Thank you.